Okay, good morning, students. So far, we have covered in our DME introduction class is factors influencing the design. Okay, factors influencing the design we have covered so far. Now we are moving to the next topic, that is the design stress and working stress. The design stress, in simple terms, we can tell that it is a value which is used in mathematical calculation of the required size of the machine member, right? It is a mathematical calculation. That's what that means. మనము మామూలుగా ప్రాబ్లమ్స్ లలో చూసుకుంటాం కదా, లోడ్ ఎంత 100 న్యూటన్స్, స్ట్రెస్ వాల్యూ 20 న్యూటన్ పర్ ఎంఎం స్క్వేర్. సో అలాంటివి అన్నమాట డిజైన్ స్ట్రెస్ అంటే. So we can consider the mathematical calculation of the required size of the machine member, that is called design stress. So in this selection of proper value for design stress is important in creating a new component, and a suitable value is arrived by evaluating the strength under service conditions. After selecting mathematical values, finally we are getting a some value. After evaluating all the values, we are getting final value, right? That is arrived by evaluating the strength under servicing conditions. So this is called design stress. Once again I'm telling you, ఇది మ్యాథమెటికల్ అంటే ఒక నంబర్ లాగా తీసుకునే వాల్యూ అన్నమాట. యాక్చువల్గా వర్కింగ్ కండిషన్ లోకి వెళ్ళట్లే మనం. సో అబ్జర్వ్ హియర్ design stress and working stress. In this design stress is based on the values, some input values. Okay, so the design stress is finally estimated by the mathematical calculations. After the mathematical calculations, we are getting the final value of the design component, right? So this is about the design stress. And coming to the working stress, so it is an actual load application we are getting this working stress. Understood? The working stress is distinguished from the design stress is the stress actually occurring under operating conditions. So design stress అనేది మనం బిఫోర్ వర్కింగ్ కండిషన్ లోకి వెళ్ళక ముందు మనము ఓకే దిస్ కంపోనెంట్ ఈజ్ అండర్ గోయింగ్ టు దిస్ టైప్ ఆఫ్ లోడ్ అండ్ దిస్ టైప్ ఆఫ్ స్ట్రెస్, this type of value of the stress and strain. Okay, after proper calculation we are getting the final value, but after designing with that value మన కంపోనెంట్ తీసుకెళ్ళి ఇప్పుడు యాక్చువల్గా వర్కింగ్ కండిషన్ లో ఉంచుతాం. వర్కింగ్ కండిషన్ లో ఉంచినప్పుడు there we are getting some other values. Okay, so design stress is distinguished with the working stress. So the working stress as distinguished from the design stress is the stress actually occurring under operating conditions. So here the workload per unit area of cross section of the part gives the working stress. We know that stress value, working stress means working load by unit area. Working stress is equal to working load by unit area. So మనం యాక్చువల్ వర్కింగ్ కండిషన్ లో ఉన్నప్పుడు వచ్చే స్ట్రెస్ వాల్యూ అంటే వర్కింగ్ స్ట్రెస్. అది మామూలుగా మనం వర్కింగ్ స్ట్రెస్ లోకి వెళ్ళక ముందే ఓకే ఈ కంపోనెంట్ ఈ డిజైన్ ఈ వాల్యూస్ కి అయితే సూటబుల్ అవుతుంది మనం మ్యాథమెటికల్ గా మనం అజ్యూమ్ చేసుకొని వచ్చే వాల్యూస్ వేరు. సో డిజైనింగ్ స్ట్రెస్ వేరు, వర్కింగ్ స్ట్రెస్ అనేది వేరు అన్నమాట. So the working stress given in the design problem is considered as design or allowable stress. So we can tell that the working stress given in the design problem is considered as design or allowable stress. We can call it as a allowable stress. So suppose that after suitable calculations we are getting the design value, design stress value 20 Newton per mm square, but in working conditions the design stress, the working stress may be 10 Newton, 50 Newton per mm square. So the design stress and allowable stress, working stress may be allowable stress. సో మనం ఇప్పుడు డిజైన్ స్ట్రెస్ 20 న్యూటన్ పర్ 20 న్యూటన్ పర్ ఎంఎం స్క్వేర్ అని అనుకుంటున్నాం, బట్ యాక్చువల్ వర్కింగ్ కండిషన్ లో అది బేర్ చేయగలిగేది ఎంత 15 న్యూటన్ పర్ ఎంఎం స్క్వేర్. ఫైనల్లీ వీ హ్యావ్ టు design the or manufacturing the component with the allowable stress only, not in design stress. So design stress is mainly It is a mathematical calculation value, right? Next, coming to the factor of safety. So in order to determine the size of the component, the maximum load that is expected to carry must be known, right? So if we are going to design a component, right? In that, for that component, how it can vary the maximum load, how much value it can be bear. Okay, so that should be known while designing a component. In order to determine the size of the component, the maximum load that is expected to carry must be known. Okay, why we have to know? Because to prevent failure of a machine part, the design stress or allowable stress at all the times must be below the elastic limit and the working stress. So working stress means stress induced in actual loading. We know already. The working stress should not exceed allowable or permissible stress. To prevent failure of a machine part, the design stress or allowable stress at all the times must be below the elastic limit, and the working stress should not exceed allowable or permissible stress. So factor of safety. How we can calculate the factor of safety? It is the ratio of ultimate stress to the design stress. The factor of safety is nothing but ultimate stress to the design stress. So by this we can get the factor of safety value. The selection of proper values for factor of safety depends upon the following factors. How the factor of safety has to be selected depends upon the material selected, which of the material we are going to use, and which type of load it can bear, and working conditions. That means it is heat affected zone or moisture zone. So some of them are, we can call it as a working conditions. Based on type of load, the following values may be selected for factor of safety. Factor of safety depends upon the material selected, type of load, working conditions. So here for steady load, the standard values for factor of safety is 3 to 4. For varying or reversal load, the factor of safety is 6 to 8. And for shock load, the factor of safety must be 9 to 16. Okay, it is a universal practice to select the factor of safety based upon the ultimate strength, and this conventional method will be adhered if nothing is specified in problem. If nothing is specified in factor of safety problem, factor of safety value, we can use these values. Understood? In universal practice to select the factor of safety based upon the ultimate stress, and this conventional method will be adhered if nothing is specified in problem. If we are we have to consider this value while doing the design problems. Understood? 3 to 4 for steady load, 6 to 8 for varying or reversal load, 9 to 16 for shock load. మనకు ప్రాబ్లంలో ఎలా ఉంటుందంటే డైరెక్ట్ డిజైన్ స్ట్రెస్ ఇస్తాడు ఆర్ డిజైన్ లోడ్ ఇస్తాడు, బట్ యాక్చువల్గా మనం వర్కింగ్ లోడ్ తీసుకోవాలి. వర్కింగ్ లోడ్ తీసుకోవాలంటే వాట్ వీ హ్యావ్ టు డూ, we have to divide the design load by factor of safety, because factor of safety is equal to ultimate strength by design stress. Ultimate stress by design stress. So we have to know the design stress, so working stress. So working stress is equal to ultimate stress divided by factor of safety. We can get the factor of working stress value. So for that reason we have to keep in mind this value. Some of the problems may be given this value and some problems may not given, but we have to observe the problem keenly, because while designing a component we have to take the working stress value, but in the problem he is given in the problem ultimate stress may be given. So simply you don't take the ultimate stress value. First you have to divide the ultimate stress by factor of safety, then only we can get the working stress value. Understood? So while doing the problem we can observe these things. So factor of safety means, so to prevent failure of a machine part, because maximum load అనేది మనకు తెలుసు ఇప్పుడు ఎంత వరకు వేరీ చేస్తుంది అనేది. మనం maximum load వరకు డిజైన్ చేయకుండా ఏం చేయాలి, బిఫోర్ వరకే డిజైన్ చేసుకోవాలంటే అలవబుల్ స్ట్రెస్ అంటే సేఫ్ జోన్ ఉంచుకోవాలన్నమాట డిజైన్ ని. అందుకే దీన్ని ఏమన్నా ఫ్యాక్టర్ ఆఫ్ సేఫ్టీ అన్నారు. అందుకోసం ఏం చేయాలి, మీకు అల్టిమేట్ స్ట్రెస్ వాల్యూ తెలిసింది. ఇప్పుడు వైల్ డిజైనింగ్ కంపోనెంట్ వి నో ది అల్టిమేట్ స్ట్రెస్ వాల్యూ, బట్ మనం ఎక్కడి వరకు డిజైన్ చేసుకోవాలి దాన్ని, ఆ అల్టిమేట్ స్ట్రెస్ వాల్యూని ఫ్యాక్టర్ ఆఫ్ సేఫ్టీతో డివైడ్ చేస్తే మనకు అలవబుల్ స్ట్రెస్ వాల్యూ వస్తుంది, ఆర్ వర్కింగ్ స్ట్రెస్ వాల్యూ వస్తుంది. ఓకే, ఇప్పుడు అల్టిమేట్ స్ట్రెస్ వాల్యూ 20 Newton/mm² అనుకోండి, రైట్. ఫ్యాక్టర్ ఆఫ్ సేఫ్టీ 4 అనుకోండి. సో 20/4 5 Newton/mm². సో ఇక్కడ మనకి ఏంటిది, జస్ట్ ఎగ్జాంపుల్ చెప్తున్నా. వర్కింగ్ స్ట్రెస్ అనేది మనం ఎక్కడి వరకు, ఇప్పుడు మనం స్ట్రెస్ వాల్యూ డిజైన్ చేసేటప్పుడు ఎక్కడి వరకు అనుకోవాలి, 5 Newton/mm² అని మాత్రమే అనుకోవాలి. అంతవరకే డిజైన్ చేసుకొని పెట్టుకోవాలి. ఇంకా అల్టిమేట్ అయినా కూడా మనకి ఎటువంటి ప్రాబ్లం ఉండదు, బట్ మనం మాక్సిమం స్ట్రెస్ అప్లై చేయాల్సింది 5 మాత్రమే అని అనుకోవాలి. అంతకంటే లిమిట్ దాటినా కూడా మనకి ఎక్కడి వరకు ఉంది ఛాన్స్, 20 Newton/mm² ఉంది, no problem. But safety, for safety measure, to prevent failure, this is the main important point here. To prevent failure of a machine part, we have to design a component in allowable stress value, right? Now coming to the simple stresses, we have already learned this topic in our strength of materials or solid mechanics, right? So depending on the direction of load, different types of stresses are induced in a component. So direction of the load, that may be axial activity, perpendicular activity, direction ante, okay na. Axial activity ante టెన్సైల్ లోడ్, కంప్రెసివ్ లోడ్, అవి అలాంగ్ ది యాక్సిస్ యాక్ట్ అవుతాయి కాబట్టి. ఓకే, ప్యారలల్ గా యాక్ట్ అయ్యే, ఐ మీన్ పర్పెండిక్యులర్ యాక్టివిటీ అంటే షియర్ లోడ్. ఓకే, సో దట్స్ వై డిపెండింగ్ ఆన్ ది డైరెక్షన్ ఆఫ్ లోడ్, డిఫరెంట్ టైప్స్ ఆఫ్ స్ట్రెసెస్ ఆర్ ఇండ్యూస్డ్ ఇన్ ఏ కంపోనెంట్. The load acting along the axis and perpendicular to the area of cross section is called normal or axial load. We know already the load acting along the axis and perpendicular to the area of cross section. సో మీరు ఏరియా ఆఫ్ క్రాస్ సెక్షన్ చూసుకుంటే దానికి పర్పెండిక్యులర్ గా, రైట్, బట్ యాక్సిస్ పరంగా చూసుకుంటే అలాంగ్ ది యాక్సిస్ యాక్ట్ అవుతుంది. సో దిస్ టైప్ ఆఫ్ లోడ్స్ ఆర్ కాల్డ్ నార్మల్ యాక్సియల్ లోడ్. ఓకే, ద యాక్సియల్ లోడ్ tending to stretch the bar is called tensile load, and corresponding stress is called tensile stress. We know ఇప్పుడు స్ట్రెచ్ చేస్తే వచ్చేది టెన్సైల్ లోడ్, కంప్రెస్ చేస్తే వచ్చేది కంప్రెసివ్ లోడ్. స్ట్రెచ్ చేస్తే మనకు లెంత్ ఇంక్రీజ్ అవుతుంది, కంప్రెస్ చేస్తే లెంత్ డిక్రీజ్ అవుతుంది. we all well know these topics, we know. So tensile stress is equal to load by area of cross section. ఆ లోడ్ ని మనం W తో ఇండికేట్ చేసుకుంటున్నాం, ఏరియా ఆఫ్ క్రాస్ సెక్షన్ ని స్మాల్ a తో ఇండికేట్ చేసుకుంటున్నాం. ఓకే, similarly in figure the axial load, so after that we will observe this figure. Similarly the axial load tending to compress the block is called compressive load. Compressive means we can shorten the length, that's why it is called as a compressive load. And the stress induced is called compressive stress. So compressive stress is equal to load by area of cross section, W by A. And next, the tangential load tending to cut or shear the part is called shear load, and the corresponding stress induced is called shear stress. Tangential load, while doing shear load, the part may be cut. Okay, if we want to divide the part into 2 parts or 3 parts, something, right, there acting the load is shear load. So that's why the tangential load tending to cut or shear the part, the part is called shear load, and the corresponding stress induced is called shear stress. Shear stress ni manam tau తో ఇండికేట్ చేసుకుంటాం, shear load by area of cross section. Okay, tensile stress, compressive stress ni sigma తో ఇండికేట్ చేసుకుంటాం, sigma t, sigma c and tau. Now observe this figure. Here we are applying the tensile load, bar and tension, because the load is acting here on this hook. And coming to here, on this is the load, this is the component. Here the component is hook, and here the component is block. So we are applying a load on the top of this block, and the floor is here. So the floor is acting force upward, and the load is acting downward. So both are in opposite directions. So for that reason, it is going to the compressive load. Here also opposite direction the load is acting. The load is acting in this direction, and the fixed beam is acting the force in this direction. So for this reason, this hook is in tension. Here the block is, the load is acting here, and load is acting in this direction. Here the part is experiencing shear. So while doing the shearing operation, the part may be cut. The part may be cut or shear off. We know all these type of loads in well known in our solid mechanics. Axial load and shear load. In axial load, tensile load, compressive load. While doing tensile load, tensile stresses happen, and in compressive load, compressive stresses happen, and while doing the shear load, we are getting the shear stress. And coming to the bearing stress, so it is also related to the compressive stress, but the compressive stress is acting equal to the area of cross section, whereas bearing stress is not equal in all area of the, not uniform in area of cross section. Right? Bearing stress is similar to the compressive stress, but the compressive stress is uniform throughout the area, whereas bearing stress is not uniform throughout the area. So this is the reason. The stress is uniform throughout, the compressive stress uniform throughout the area is called compressive stress, whereas the component experience compressive stress but not uniform throughout the area is called bearing stress. For example, force exerted by a journal on curved surface bearing. Because load is not uniform, the projected area of the curved surface is considered as equivalent area on which the stress is equally distributed. So ikkada manaku uniform ga ledu, projected area vachindi kabatti manam emannukuntam which ekkadaithe equal ga undo akkade surface area ekkadaithe same undo, so ఆ స్ట్రెస్ నే మనము కన్సిడర్ చేసుకుంటాం. బట్ యాక్చువల్ పాయింట్ ఆఫ్ వ్యూ ఎలా ఉంది, సమ్ ప్రొజెక్టెడ్ కర్వ్డ్ సర్ఫేస్ అనేది వచ్చింది component నుంచి. Understood? So thus the bearing stress can be obtained by using the relation load by projected area, load W and D by L here. So this is the D value and L value, diameter D and length L, right? Next, coming to the strain and elastic module, we know as a result of tensile load, the bar becomes longer, or due to compressive load, the bar shortened. Due to tensile load, the bar the length may be increases, and due to compressive load, the length may be shortened. So this change in length per unit length of the bar is called unit strain or simple strain. So we can easily tell that delta L by L within the elastic limit, the stress produced is directly proportional to strain. So that is the Young's modulus. Stress is equal to a constant into strain. A constant means we know it is a Young's modulus. Young's modulus is equal to stress by strain. It is represented by E, Young's modulus. Similarly, the ratio of shear stress to shear strain is called modulus of rigidity. Next, bending. When a beam is subjected to a simple bending, the stresses that are induced are a tensile stress on one side of the neutral axis, bending, right? So bending means లోపల ఉన్న పార్ట్ ఏమో కంప్రెసివ్ స్ట్రెస్ కి లోనవుతుంది, బయటకు ఉన్న పార్ట్ ఏమో టెన్సైల్ స్ట్రెస్ కి గురి అవుతుంది అన్నమాట. సో when a beam is subjected to a simple bending, the stresses that are induced are a tensile stress on one side of the neutral axis, a compressive stress on other side of the neutral axis, and the shear stress induced is small and can be neglected. We can neglect the shear stress value. The bending moment at any section of a beam is the algebraic sum of all the moments of the external forces acting on either side of the section under consideration. మనం bending moment equation రాసుకున్నాం కదా, W into D అని, load into perpendicular distance అని. So the bending moment at any section of a beam is the algebraic sum of all the moments of the external forces acting on either side of the section under consideration. ఇదంతా మనము సెకండ్ చాప్టర్ లో సాలిడ్ మెకానిక్స్ లో చేసిన ప్రాబ్లమ్స్. So we are getting a bending equation that is m by I is equal to sigma by y. M is equal to sigma into I by y, where m is equal to bending moment at any section, and I by Iy you can call it as a section modulus. We can indicate with a z value. So m is equal to sigma into z is the bending moment equation. I is equal to moment of inertia of the section, mm power 4, then units sigma Magnus stress at outer fiber Newton per mm square, y distance of outermost layer from neutral axis, and the term I by y is called section modulus and generally represented by z. We know already. It should be noted that this expression is applicable only to symmetrical sections, as y may have two values for other sections. The expression sigma into I by y is termed as resisting moment. While designing a beam, it is important to note that the resisting moment must be equal to or greater than the applied bending moment m. ఈ వాల్యూస్ అన్ని మనం నేర్చుకునే ఇక్కడ కొంచెం మిస్టేక్ పడ్డాయి. ఫర్ రెక్టాంగులర్ సెక్షన్ BD square by 6 ఇది, and here BD cube by 12, y is equal to d by 2. After calculation sigma into z, z అంటే BD square by 6, b is equal to width of the section, right? ఇవన్నీ మనం చూసినాయి. Next, the shear stress is induced in a member due to twisting moment. So T by J is equal to tau by R అనేది torsion equation. T అంటే torque applied Newton mm, J polar moment of inertia mm power 4, tau shear stress induced Newton per mm square, R is equal to radius mm. The term J by R is called polar section modulus and is represented by Zp. Thus T is equal to tau into Zp for solid circular shaft of diameter d. Zp is equal to pi d cube by 16, J is equal to pi d power 4 by 32, R is equal to d by 2. For hollow circular shafts of external and internal diameters d, O and di respectively, Zp is equal to pi d. ఇవన్నీ మనం చూసినాయి బాబు, కొత్తగా నేను ఇప్పుడు ఇక్కడ ఏం చెప్పట్లేదు మీకు. pi d 4 అన్ని చూసుకోండి ఫార్ములాస్. This is all not new for us. And combined flexural and bending torsion equations also. So for this we can finish the design stress and working stress and loads and stress values, right? So now I am going to close this session now. Thank you.